This planet uses a lot of energy, or at least we humans do. According to the most recent International Energy Agency report, we consume 157,000 terawatt-hours of energy every year. To put that number in perspective, that's actually equivalent to 90% of the solar radiation that falls on the Earth in a single hour. Granted, we only harvest a small fraction of that using solar energy, and we're not really going to talk about that right now. Instead, I would like to inform you of the thermodynamic process that drives the majority of our baseload power plants. Baseload power plants refer to plants that are able to constantly provide some baseline level of power to some region. These are in contrast to peaker plants like solar energy stations because they aren't subject to variables that could reduce their power levels. The vast majority of our power plants come down to one basic principle in thermodynamics. The majority of our power is produced by plants that follow one idealized thermodynamic model known as the Rankine cycle. It describes a steam engine's behavior in the most ideal conditions. Thus, the general principles are as follows. There must be a coolant input. This is generally water. This is then pumped through a heat source, which causes the fluid to vaporize. The newly vaporized fluid is pushed through a turbine. This turbine extracts the kinetic energy from the steam, and then it is converted to mechanical energy. This newly condensed steam that has lost its energy will go into either a condenser or some out. Ideally, just the temperature input and output determine the maximum efficiency of your machine. However, we know the real world isn't always the generalized case. Thus, the Rankine cycle is just sufficient to determine what we could hypothetically get, but not necessarily what we will see. A nuclear reactor is merely one out of many examples of the applications of the Rankine cycle. If one performs the theoretical calculations, it generally comes out to about 63% as the maximum efficiency. However, for nuclear plants, it's actually about 33%. That's quite a drastic difference, but that's because there are a lot of engineering problems that aren't accounted for in the idealized case. The video would be much too long if I decided to talk about all kinds of nuclear reactors, so let's just focus on boiling water reactors, or BWRs. Of course, our journey begins at the cooling inlet. These power plants are extremely water hungry, and they are generally situated around some water source where they have their very own elaborate cooling pond. Either way, whatever temperature of your externally influenced water source is, whether it be artificial or natural, that's what you get. Depending on the cooling configuration, the massive intake pumps can provide the reactor vessel with 100,000 gallons of water a minute. As the water floods the reactor vessel, it surrounds the core, which is constantly converting mass to energy, as we discussed in this video. The heat produced from the nuclear fission occurring is transferred to the water, which is then vaporized. This steam is then pumped into a turbine, which spins to extract the kinetic energy from the steam and convert it into mechanical energy that we can use for our laptops, lights, and cameras. The steam that has reduced energy is then pumped either through a condenser or it's let out back into the environment after passing through cooling ponds. Nuclear power supplies about 10% of the world's energy, and it may be on the rise as long as climate change continues to make us feel the heat. It may be the base loading system of choice for a while, or at least until we're able to get a working fusion reactor or perhaps better battery technology to better utilize wind, solar, geothermal, and all of that. I will talk to you soon. I hope that you stay safe, my witchlings, and know that you are incredible. Until next time, bye.